So Joydeep, please continue.
Can I start?
Just 1 second. Just kindly again, maybe you have to do it again. Make Orko co-host again.
I think I have made him
Yeah,
code.
maybe, but it has, I think, yeah, it was, yeah, disconnected and.
Okay, let me. Yes.
Yeah. Okay. Okay. Yeah. Let's continue. Yeah.
Okay.
Mm.
Okay, Sanjay. Thank you. So today we'll continue whatever we have discussed last time, and we have actually initiated that part. So it's effectively the it's integrating out and those heavy fields and all those things. So let me summarize that part. So you start with the UV theory, and then you integrate out those heavy modes. Okay, you perform the matching, and then you basically get the effective action. But with that effective action, it's not sufficient to work with, because some of the operator and the structures are related to each other. So what you have to do, you have to explicitly impose the equation of motion, and you have to use the integration by parts, Fears identities, and so on, to get the effective action or the set of effective operators which are basically independent. And then we have seen that, okay, so this example, that if you start with our UV theory, and then if you want to look at the standard model scattering, basically your asymptotic states are basically standard model. So all the new physics will be basically as an intermediate state. They are not appearing as a asymptotic states. And then what you can do, actually, you can integrate out those new physics modes, and then effectively you are getting the effective operator and along with the standard model. So this gives you an idea why this is the complementary to the bottom-up approach, because bottom-up approach, we added this quantity along with the renovable part, and such that we expect that these together can grab any effect in the new physics which is written in this particular form. But in the top-down approach, the other way around, you start with this new physics involved diagram, and where you integrate out the new physics part, and effectively you are writing in this particular form. So this actually gives you the complementary vibe of these two approaches, right? But let me recollect again that here the Wilson coefficients are basically function your VSM parameters, and the cutoff scale is associated with the mass of the heavy fields that you are integrating out. So then we briefly discuss that, okay, so if you start with a UV Lagrangian, our primary focus will be only on that part where the heavy field is involved. For example, here we have this capital phi is the UV field, and then they have a self-interaction, and then the mutual interaction part is this one, right? And this mutual interaction part, you can write down, or you can think of like a polynomial in heavy field. For example, it can be linear, then quadratic, and then trilinear term could be there. And as we are expecting to start with the UV Lagrangian, which is renovable, having dimension 4 up to dimension 4 operators. So this cannot contain more than that, right? Because the quartic part is already here. And now we also assume that in the interaction part, there is no derivative involved. So we can use our usual minimal form of the Euler-Lagrange equation. And from there, we can write down the, this equation of motion for the heavy field. And then inverting this operator, we can find out the classical solutions, which we treat as a background. Why background? Because background field, naively speaking, they do not have any kind of dynamics, right? So this heavy field, we can expect as so heavy that it doesn't have any background, and all the light fields are basically the dynamics are on the background of this heavy field. Okay, and then this is also a solutions from the Euler-Lagrangian equation. Now, once you do that, so this is still basically in terms of a the non-local form it's written. But now when you can expand this structure, here the assumption is m, which is the mass of the heavy field, is much greater than any kind of momentum transfer in the system, right? And that's why you can perform a binomial expansion in the inverse mass square, and you get this term. So you can certainly have more, 1 by m^6, 8, and so on terms, but we can truncate here. And then depending on what kind of operators, that means which dimension operator you want to generate, So you will truncate your this phi c there, and then you plug in that phi c in this Lagrangian, and from there you can compute the effective operator. Now, in this particular case, if you see that here there is no quantum corrections or loops, any kind of involved, right? And this is just a expansion of the interacting propagator of the heavy field. Why interacting propagator? Because this involves the interaction. If you remove this term, this is the free propagator of the heavy field. And also here, one of the important part is the presence of this B. So B, if you see, and what is this B? B is actually function of the light fields, but more importantly, it contains the heavy field as a linear order. That means if there is no interaction term where the heavy fields appearing as a linear along with the light degrees of freedom, then we cannot generate any kind of effective operators at that T level. So this will not be possible to generate in this way. And we expect the generation of the effective operators at the higher order or more. So this is the identification of the which one is the Wilson coefficient of the effective operators. So then whatever we have learned in that slide, we try to understand through a explicit example where you consider the heavy field as the phi, okay, and it is like a color singlet, the isospin doublet and hypercharge minus half. That means you have introduced the heavy field which mimics the standard model Higgs, and that's why there is some kind of interaction term. And if you do not impose any kind of Z2 symmetry in your Lagrangian, then you can have this trilinear interaction. So trilinear in Higgs field, but linear in the heavy field. That's a total quartic interactions. And eta h and eta phi, they're basically dimensionless coupling. And then you have this, lambda 1 and lambda 3, which are basically also dimensionless coupling. Now, if you try to go back and to the previous slide and try to map what is my B, so you'll really identify B is nothing but this term, right? This eta h times this h cube order term, because it's a linear in heavy field. So if I use this phi c definition that we have derived in the last few slides, then you can say that okay, phi c is this, and once you plug in there, then from these interactions will generate basically an operator which has mass dimension is 6 now. That means you start with a renormalizable term involving a heavy field, replace the heavy field by its classical solution, which is generated by the covariant additive expansion of the propagator, and then you generate this term. And then you can see that this is proportional to the eta h. So eta h actually contained in B. So what we are claiming that if there is no B term, we cannot generate this operator that is reflected from here. If eta h equal to 0, we cannot generate this term in the T level. So one of the bottom point that we understand here that to generate a T level operator, we need to have an interaction where the heavy field is appearing linearly and all other fields are basically light fields. Okay. So now let me give a pictorial notion what we have done in the previous. So the meaning of covariant expansion is basically integrating out, okay, or it's like expanding the propagator at the T level. So now, pictorially, if you try to understand this point, how to do that? So if you see the Lagrangian and you try to calculate the Feynman Bartes factors, then you'll find out that the quartic scalar interactions is there, and this quartic scalar interaction is such that there are 3 light fields and I have 1 heavy field. Now, if I have this kind of Feynman vertices, we know even it has nothing to do with the effective field theory. It is generic structure of the quantum field theory that if you know the Feynman vertices and the propagators, you can glue them in such a way that you can generate the processes. So now I glue these this kind of vertices twice and I generate this diagram. So you can think of this like a external state has the 6 Higgs fields, okay, and they're exchanging in heavy scalar, heavy Higgs doublet, right? And that's why in this process, if you see, I mean, this like a propagator is basically 1 by p square minus m phi square, and where m phi is the mass, and where the m phi is much larger than the momentum transfer through this. And if you calculate the amplitude of this process, okay, and then if you assume this in the leading order, you will get a term which is basically eta square by m phi square. So the notion from the diagrammatic point of view is that basically you calculate the endpoint amplitude for the UV theory, and then in the UV theory in such a way that all these endpoint asymptotic states are basically my light fields, and you calculate all the tree level, you draw all the tree level diagrams, and after that you squeeze the propagators. If you see, when I'm doing this to this, I'm actually taking this space-time point and this space-time point to be together. This is like taking a coincidence limit. Okay, so if you think the Green's function is like a gx comma y, this is like a gx comma y. I'm taking this x tends to y limit. So this is the actually field theory equivalence is basically expanding the propagator. This is a non-local thing. I'm making it local because x tends to y. The things are becoming local, right? So now, if I take if I take the calculate amplitude, and this amplitude is nothing but the Wilson coefficient of this endpoint, operator, and that's how diagrammatically it actually works. But when for a realistic situation, you can encounter lots of diagrams, so that's why that we may require an alternative approach instead of drawing a diagram, more algebraic way to calculate that thing, and that's what we'll learn. But yeah, before proceeding up to this part, if you have any question. Okay, so let's proceed. So now
why you said it's non-local?
Sorry?
Why you said it's non-local?
Because these are two different space-time points up here. That's as a non-local. And from expansion of the propagator gives you basically squeezing the x, y, and then you take an x tends to y limit, and that's why you get basically the point interaction.
Yeah, but
that's the local interactions.
But normally, if we have a let's say Feynman diagram, there are two vertices, right?
Yes, two different vertices.
Yeah, so that is in normal situation.
Yeah, like a Green's function. Green's function carry the information from one space-time point to another space-time point, right? So if you think about, like, for example, weak contraction. One is 5x, one is 5y.
Okay.
Right? So that's the Green's function gxy. So now, what is the meaning of this expansion of the propagator? Is basically taking the limit from x tends to y. And then you basically rewriting these non-local terms in terms of infinite terms in terms of local operators, local structures.
Yeah, but if you have infinite number of derivative operator, that is still non-local, right?
Yes.
Infinite number of local operator with derivatives.
Yeah. So this particular, so with this I'm truncating here. That's becoming non-local. But if you add much more higher order expansion of the this operator, this will be p square by m5 to the power 4. Right? And then P4 to the M5 to the power 6 and so on. So that will not be a 5-6 operator. That will be 5-6 G2, 5-6 G4, 5-6 G6, those operators. But each are basically non-local operators. But sorry, each are basically local operators. So then from the non-local, you get infinite number of local operators.
Yeah. If they're not truncated at finite number, then
yes, exactly. And because here the derivative actually contains that momentum information of the external states, so that's why we assume here that the momentum transfer is small. So that's why we can truncate, because this is a convergence series.
Oh, what you are saying actually in the diagram in the left or right, whatever your left, my right, is non-local. Whatever written non-local, that actually the propagator will be expanded, and that is basically non-local interaction.
Exactly. So this is one of the operators. So this is not equal to this. This is generated from this. But if you want to write down all the terms, you'll have an infinite number of terms.
Yeah.
Okay. Okay. Yeah. Is there any other question?
Not from me, but yeah.
Okay. Okay. So now, so whatever we have done so far, we are thinking about the tree-level expansion. But as I told you that if in your theory, if interaction, if you have a big term or which is a linear in heavy field, then only you generate basically, this tree-level operators. But as you can see by writing or your theory, or consulting some different literatures, that there are not many models offering this kind of thing. So generation of tree-level operator is rather a very limited option you have, but most of the theory do not contain, because of the conservation of the quantum number, the symmetries and all those things, they do not have this linear kind of structure. And also if you impose the discrete symmetry to discard them, then the leading order generation of the effective operators will appear at the loop level. So that's why knowing the tree-level integrating out may not be sufficient, rather it is very restricted to specific kind of situation. So to have a generic idea how to generate the operator, we must look beyond this tree level, which is the loop level, and that's what we learn. So these are the different kind of topologies that you may encounter. So the first one is basically tree level, right? Where the new physics is basically a tree level propagator, so that you are now familiar with. Now in the loop level, you may encounter two different kind of topologies. In one kind of topology, where in the loop, all the propagators are basically heavy fields, right? So now, what is the easy part of this thing? That if all the propagators are heavy, then the way you have squeezed this, heavy propagator in a previous method, we can perform the expansion and we can then truncate suitably. That you can do. So basically, you squeeze this, you get an effective thing. This you squeeze this one, you squeeze this one, and this one, because all are basically massive. So eventually, I can replace all this propagator by its classical solution, and I get the effective operators from this. So that's
Joydeep, but there is this undetermined loop momentum, right? That is there.
Yes.
Let's say one of these propagator, new physics propagator, has a undetermined loop momentum, let's say K, and then the rest of them has some other momentum leveling depending on whatever is the incoming, outgoing momentum. So this undetermined loop momentum need not be less than the mass of the heavy particle, right? So then what to do? How to kind of integrate out that propagator?
I understand. Okay, so that's what you are saying. That's a basically working way to do that thing. So basically, you have to perform the momentum integral and all those things there. Okay. But what I'm saying that how to demo, I'm trying to demonstrate you this thing. So basically, the loop moment, the expansion, okay, still you can do in the new physics actually, because this covariant derivative which is coming from here, they are actually acting from the heavy field, okay, and their momentum, not the loop momentum, but the other. So you will perform the expansion. This expansion will involve your loop momentum, but your expansion, the del square is actually signature of the external state momentum. So the expansion, when I'm performing this p square by m square, that p square is the external momentum. So that's how you will expand. But it will contain basically the loop momentum, and eventually you will perform the momentum integral. And that will give you a finite quantity.
Not quite clear, but yeah, if you can later on explain, maybe or in a...
No, it's a simple thing. So the new physics, so there's a two momentum are involved here. Okay. One is basically the loop momentum, one is the external momentum.
External momentum, yeah.
Right. So you will perform the expansion about the external momentum by m square, because that will give you the operator. The del operator that we'll be talking about, that del doesn't correspond to the loop momentum.
Sure. No, I'm just saying, let's say if I label all this propagator, right, intermediate state with some momentum level, one of them I can choose to be some arbitrary loop momentum K, and then I reminder of these propagators can be labeled accordingly. Now the propagator for that one, which has a label K, will be just, let's say, 1 over K square plus m or minus m square, right? So now what to do in that case? For that propagator.
You see, so when you do that thing, so I understand your question. So what I'm saying that the way I'm demonstrating, it is not computed that way.
Okay.
It is a notion how to get the local operators out of that, because you can squeeze. So when I'm saying that I'm squeezing them, it is not like I'm squeezing one by one. I'm squeezing all of them simultaneously. So when you write the momentum integral, is a product of, let's say, 4 propagators. you write down the product of the four propagators. If you want to write down a diagrammatic method, you write down a Feynman parameter form, okay, and then you perform the expansion of our k square, where k is the external momentum, k square by m square. You perform the denominator in that binomial expansion. It's not like individual propagators you are expanding.
Okay. Okay, we'll continue maybe later on.
It's like so whatever the denominator you will get in the after calculating the loop momentum, okay, that denominator will be function of light moment, loop momentum, external momentum, and the heavy mass. Okay, and then you write it down less for the function of light internal momentum plus some external momentum square plus some m square. Then you take out the m square. Okay, you get basically 1 plus k square by m square plus some term, and the k square by m square, where the k is external momentum, you will perform that as an expansion parameter, which is a small one.
Okay.
For the loop momentum, you have to perform the integral first.
Yeah. No, I'm just this k is your loop momentum or the external momentum you're saying? This k square by m, so this k that you are
this k is the external momentum, not the loop momentum, because I have performed the integration of the loop momentum.
Yes. Okay.
So when I perform the loop momentum integral, there will be no relic of that. I will be left with the external momentum and the mass of the heavy field. Okay. And that's what I can expand now.
Okay. No, so is there any, I'm just maybe one more question on this.
Yeah.
Is there any ordering thing you are also, you perform the loop integral, then whatever is left, then you do this expansion, means approximation. That's what you're asking?
Yes, that's what we do.
Okay.
Yeah. So we get rid of the loop momentum.
Okay. So then there'll be only this external momentum and
the... we don't need to worry about the divergences, because at the end of the day, you are generating an effective operator. If you focus on the effective operator part only, that will be always finite.
Okay.
Okay, so there's no divergence associated while generating the effective operator. There will be divergences, but that will be dumped in the reversible part.
Sure.
Okay.
Okay. Thank you.
Okay. Yeah. But now there's another different kind of topology involved here, which is in a loop, you can have a new physics propagator as well as the standard number propagator. Now, the problem is basically you can think of writing this new physics propagator, in terms of a infinite expansions in terms of local one, but not the light particles, because the light particle masses you cannot do that thing, and that's why this kind of loops offer you two contributions if you really calculate. One contribution will be local contribution, one contribution will be non-local contribution. And how to compute that thing, that's a slightly different way one has to calculate the integral. There are different methods of doing that thing. Okay, maybe when I talk about, if I get some time later, I'll talk about how to calculate these loops and all those things. But what is the important basically, here the expansion we perform in terms of this k is the external momentum, k square over m square. But here we can get the contribution to the effective operators only that regime of the momentum where the momentum is much larger than the mass of these particles. So that means here we have an invert expansion. The m is the light mass, m square over the p square, where p is the large mass, or in the domain of the large momentum actually. So p generally runs from 0 to infinity. So then you can decompose that regime. It's like a methods of region, actually, the way you do that thing. So you truncate, you just make it 0 to lambda and lambda to infinity. So 0 to lambda, if you get that integral, you will get a non-local contribution to this operator. But the lambda to infinity, and in that regime, if you perform the integral, then you will get a local contribution. But this is a more diagrammatic way of doing that thing. But certainly we will not do diagrammatic method, because that is very tedious doing that thing. So we'll alternate that. But diagrammatic methods are very, important to understand what is going inside. So that's why this is called the light-heavy mixing contributions. Okay. So these are the slightly difficult to calculate compared to this. But there is no reason that these Wilson coefficient generated from these diagrams will not be as useful as this. They're equally useful. Sometimes, for some operators, you get contribution from this only. It may happen depending on the interaction. So one should not be ignorant about these kind of contributions, because earlier literature, if you see, these kind of contributions were ignored, but later it has found that they are equally important to compute. Okay, so these are three different topologies you may encounter. Okay, so when I'm saying different topologies, you may have 3 new physics, 1 light field. So what I'm saying that this is different than this, that in the loop you have at least 1 light field, and that makes it different topology than this one, where you have all are heavy fields. Okay, yeah, up to this part, you have any question? Okay, so once we have this ideas of what is the tree level, what is the heavy loop, and what is the heavy light mixing. So now, what we'll do, instead of doing for this diagrammatic approach, we use the background field method and we use the functional method. So now, as you know, we have this action. The action is basically written down for the UV theory, which is basically functional of light field and the heavy field. And now we treat the heavy field as my background. So now to input the quantum corrections, what we have to do, we have to actually consider the fluctuation, quantum fluctuations corresponding to this background field of the corresponding to the heavy propagator. Okay, and that's what we do. So phi c is the same what we have discussed corresponding to the heavy one. So we know what is my phi c. Okay, and then we perform a Taylor's function. Okay, and then if you perform the Taylor's function, then you first write down this term. Okay, and then the second one, this, the first functional derivative, and then the second functional derivative, and so on. Okay, and then this quantity doesn't include your eta. So basically, this is basically as similar as what we have discussed at the contribution from the tree level diagram. So that we have learned how to do that thing. Now, what about this one? This is identically 0 at phi equal to phi c, because using the power of the Euler-Lagrange equation, because this is how you calculate your phi c. So next dominant contribution is from this one. Now this is a functional derivative, right? So then how do I know that this is equivalent of one loop calculation? I am not especially showing this thing, but it's up to the students. You can find it out in the literature, and it's common literature now, that is what we generally said while computing, that we set our, for the natural unit, we set h bar equal to 1, c equal to 1, right? So now, if you do not do that thing, now when you write down the S matrix and so on, then this action is basically scaled by the h bar. Now what you can do, if you put this h bar explicitly, then automatically your fields, couplings, everything will be suitably scaled and associated with the h bar. And keeping that h bar, if you perform the expansion, then you'll find out that this term is proportional to h bar to the power 0. That's why this is called the tree level or the classical contribution, and this is proportional to the h bar. And that is the signature of the quantum. And h bar is a universal parameter. In this formalism, if you are familiar with this functional method, in this formalism, h bar is used as a universal parameter to count the loop. Okay, so that power of the h bar tells you that if I calculate this, then I don't need to calculate the loops explicitly. This gives me the equivalent contribution of one loop. And similarly, you can go beyond that and you can calculate higher loops as well. But of course, those are more difficult. But what is important, that what we have learned, that okay, there are some loop diagrams. We don't know, we can calculate the explicit loops and calculate the effective operators. But if you are familiar with the functional method, then we rather use a functional derivative instead of calculating the loops and all those things, and compute the effective operators. Okay. So this is how we'll calculate the loop contributions. Yeah. Any question? Okay. So now, if I do in a much more integral form, how do I write it down? So as you can see, this is the way we write down, and this e to the power I is effective, because the effective action, because this is function of your light fields only. which is nothing but you are integrating out the heavy fields, and that's where the name integrating out is coming. It's not just the name, it's actually you are really performing this function integral. Okay, and then what you do, you actually expand this and you stop here because you want to calculate up to one loop. Okay, and then if you calculate this integral, what you calculate, then this it is basically give you the determinant of this operator, which you can write down as a determinant of any operator. You can write down e to the power trace log a, and from there, if you write down, you can write down in terms of trace log of this operator. And eventually, if you see what is this action in general, when you write down, it's basically d square plus m square plus q, which is sandwiched between two heavy fields. Okay, and then if you take a functional derivative with respect to phi, you pick out this operator. And that's why this is equivalent to this. And from there, you can write down the effective action is nothing but the trace log of this operator. What is left to is that to calculate only this quantity. And once you compute this quantity, you actually compute all the one loop generated effective operator. And that's how we calculate the one loop effective action. Yeah, up to this part, any question? Okay. So now, but as you can see that computation of, this quantity is there, of course, but eventually we had to calculate this thing for different theories, because the purpose will be revealed soon. So that's why it's better that we can plug in and develop an automated program based on that, such that we can compute this thing. And that's the attempt is there. So what we do actually, we have developed a program which is based on this covariant derivative expansion, and which compute this one loop Wilson coefficients for any kind of extension of the standard model. It's mostly work for the scalars, and also now it's also work for some of the Fermion theories as well. So in this program, codec, it actually calculates the Wilson coefficient, and from there you can calculate the tree-level operators only, or also operators up to one loop. Not only that, if you remember, the matching scale is basically lambda, where lambda is the cutoff scale, right? But your exponential data that you are using, that may be at much below scale, right? So then, in principle, you have to bring all the operators to that low scale, apart from the fitting and all those things, okay, to adjust and their impact in the context of data. So that's why you have to perform the running of those effective operators. And here, this program also has the provision, then you can run down those operators at the low energy scale. And that's the, starting from the integrating out, to run them down to electric scale, you get all the operators in the process. So now let me give you a tentative idea how this works. So in this program, if you remember the previous program, we have shown different kind of input file, how to do that thing. Similarly here, you have to define the heavy field. You have to given some specific your preferred name. Okay, how many components are there? For example, if you have a Higgs doublet, then I call it a Higgs, but Higgs is already there, so it's a defined name F. Let's HF. Okay, and then we have the component, two components are there. It is colored singlet, so one isospin doublet, so two is the hyperchar minus up, and there's a mass parameter is MH2. And then we define the heavy field as the phi, having all these quantities in quantum numbers, the mass parameter, and the name. And then we write down the BSM Lagrangian. If you see, we do not need to provide the standard model Lagrangian. We provide only that part of the Lagrangian in the input file that involves your heavy field. And that's what we have done. Okay. So now if you're making a mistake in providing this thing, you'll get a wrong answer. So you have to be very careful that you know the correct Lagrangian. Okay. And once you know this correct Lagrangian, then basically this thing that you write in a pen and paper, but you translate this in the input file in this particular format. So this is the defined way to demonstrate actually. There's a lot of examples are given. So from there you can learn how you can enter this Lagrangian in this particular format. So this is the input Lagrangian you are providing, right? And once you provide that, then you can ask for the output, okay? And if you remember, ask that, okay, give me only the tree-level operator, okay? Not only that, as I told you, like in vector space, you have a different choice of basis. Here also, in the operators from a basis, you have a different kind of choice. There's a called a strongly interacting light higgs or SILH basis or Warsaw basis and so on. So if I say Warsaw, it will give the results in the Warsaw basis. If you say SILH, it will give the result in the SILH. But remember, SILH doesn't include the Fermion operators, so it will find out less number of operators actually. So let's look at the Warsaw one, but also tree level. Now you can see in this looking to the these are the wheels, these are the operators, and you'll get the output particularly in this particular form, which is very easy to understand which operator and the Wilson coefficient. So you generate these operators at the tree level. So 5 to the power 6 or H dagger is whole cube operator will be generated at tree level, and it will be accompanied. Wilson coefficient will be this, right? And then you can see that all the operators are involved. There is no pi involved. So that means all are basically tree level generated operator. Okay. And now you can see this operator. See the Wilson coefficient. How do you expect that you have a H dagger H, and then you have a heavy field, and that is interacting with this part. So this YH2 is the Yuka coupling, which is basically interacting with this sector, and ITIJ is basically that linear coupling, the quartic coupling, dimensionless quartic coupling, which involves these 3 Higgs cells, right? So that's how the Wilson coefficient is expected to be a product of these 2 couplings divided by mass square, and that's how you get this thing. Similarly, you have these 2 currents. So now looking at the gamma mu, you may think this is scalar, but how this gamma mu is appearing? Because for the 4 Fermi theory, you know there's a heavy gauge bosons. But you can use the Fierce identities, and from there you can write down this kind of vector current in terms of harmonic current extended by the scalars as well. So that's why you would expect them, the Wilson coefficient to be proportional to the 2 Yuka couplings corresponding to L and E, okay, and then suppressed by the L square, and that's what this is 2 Yuka coupling square. And this is the Yuka coupling the quark sector, and that's how. So basically, just looking into this Wilson coefficient and the operator structure, you can assume, right? You can really understand that, okay, so is that aligned with your expectation or not? Then you'll find out that actually, if you do calculate in a correct way, you'll find out they're consistent with your expectations. Okay? Yeah. Up to this part, any question? Okay. So now this is a tree level thing, right? And as I told you, SILH contains only the bosonic sector of order. Now recently it has been extended to fermionic part. But when you developed SILH, used to contain only the bosonic part. So it offers you only the O6 operator. Because all other basically my harmonic involved operator. So in the SILH basis, you will find out only one operator. Right? So now, how do I calculate the loop thing? For that, you need to provide this out range, which was earlier tree. Now this is like a loop. So once you do that, you basically get the loops. Now you see at the loop level, you generate so many operators. And the signature that looking to the Wilson coefficient, how to understand that they are loop generated, the presence of pi square. Because this is the 16 pi square of the loop factor. This is the origin of that thing. This is a clear-cut signature. This is generated in the loop level. Okay. And this is also, remember, only those loops where we have only the heavy fields. Okay. So now you can see initially we have only these many operators at the tree level. And once you allow to generate loop, then also this thing. Now you will find out some of the operators are common here and there. For example, this phi-6 operator. The phi-6 operator generated at tree level, also at 1 loop level. That means if you calculate with a better precision up to 1 loop, then some of the operators are not only generated at loop level, at tree level, but also there are some additional contribution from the loop, and you have to include them. So effectively, up to 1 loop, the phi-6 Wilson coefficient is basically the previous tree level generated plus this one. Okay. So in this way, you can see that there are lots of operators generated, and if you have more operators, that imply they are participating in more processes, and that's why the more observables you can calculate. And in the loop level, you can simultaneously calculate the SILH basis operators, and you'll find out some of the operators which are generated here. And one of the interesting observation is that in these operators, there are parameters like eta is 2, lambda is 2, 1, y is 2, and so on. These are the BSM parameters. That means the contribution from these operators can be controlled by the BSM parameters. But there are some operators generated. They have nothing to do with the BSM parameters apart from the mass of the heavy fields. They're function of the standard model couplings, right? So you don't have much handle to them. So if these operators are very tightly constrained, then that will tightly constrain your MH2, and that will passively, affect the fitting of these parameters as well. So that's why while performing in analysis the data, one has to be very, very careful. Yeah, up to this part. Any question? Okay. So now, as I told you that this is a one loop, but these loops are basically consist of only the heavy propagators. So what about the contribution from heavy light diagrams? Heavy light diagram, just to recall, these are called the heavy light diagrams, where in the loop you have at least one light propagators. If you do include those contributions, and then you'll find out there are some additional contributions to the existing operators in terms of Wilson coefficients, which are basically the light heavy mixing. And once you include them, then you can say up to one loop your integration out is complete, and you get the complete Wilson coefficient corresponding to each and every operator. And then your contribution analysis will be more robust in that. You are not missing out anything. Okay. So then these all the operators are generated at the one loop at some lambda scale, right? And then, as I told you, at the end of the day, you have to see the status of these operators or their contributions. If you have to really adjust their impact, we have to bring them to that scale where the data is being collected. So if my lambda is basically few TeV, let's say 5 or 10 TeV, then my electric data, the Higgs signal and electric fission data are basically at the electric scale. So I have really run those operators, and while the running, this running is being done by this calculating the anomalous dimension matrix associated with these operators. Okay, so these anomalous dimension matrix are basically not diagonal; they have off-diagonal entries. Now, what is the meaning of that? It means basically, if you consider the running of the operator 1, then it will mix with other operator O2, O3, and O4. So that's why it may happen that after integrating out, you may get, let's say, few number of operators, but when you perform the running additively or through the running, you may generate more and more operators. And that's what it is shown. For this particular case, you are generating through the one loop matching 37 operators, but if you perform the RG running to the electric scale, you will generate 48 such operators. And that 48 operators, you will find out what kind of observers you are considering and whether all the operators are contributing there. And that will be effect of your one loop matching plus the RG effect. And that will give you the neat and clean picture and more robust analysis. Okay. So this is the prelude of the phenomenology. But yeah, any question up to this part? Okay. Am I audible or not?
Yes, yes.
Okay.
Yeah, I'm just asking, this RG flow is from matching scale to electric scale?
You can set the low scale anywhere. It's
okay, yeah. Yeah. But it will start, what is the starting point? Let's say
starting point is basically your basically MH2.
Okay.
That's the cutoff scale.
The cutoff scale. Okay.
From the cutoff scale, and then you set this mu, so you'll get operators, and then you can get the result, which is function of log of MH2 by mu, and you can choose your mu to be electric scale or whatever you want, where you perform the analysis.
Yeah, just one think since the number of operators are different, it's 37 versus let's say 48. So
Mhm.
some of the operators are not present at, let's say, at a scale MH2. Most of them. So then I'm just trying to understand. If it is if we're doing top-down approach,
Hmm.
okay, and let's say at that cutoff scale, I have
Hmm.
these 37 operators,
Yeah.
okay, and then I'm just studying how how the let's say this Wilson coefficients are actually coming out to be at a electric scale or some low scale.
Yeah.
So this 48 operator that I'm getting,
Hmm.
it's coming from this 37 sub. It's that.
Exactly.
Yeah. Yeah. Uh,
So, are you worried about what is the Wilson coefficient of this additional operators?
yeah. And yeah, one
Okay.
of them is that.
Yes.
Yeah.
Let me tell you the details. It's good that you have raised this question. So that is the beauty about this, or beauty or the difference between the top down and bottom up. So when you perform I will show the analysis, then it will be much more clear. But because as you have raised this question, let me give you some pinch of salt of that answer actually here. So when you are doing basically the bottom up approach, okay, and if you remember the first day, there's a question about the renormalization of this thing, right? Now, when you have this bottom up approach, if you do not include the complete set of operators, you can generate some operator, okay, and which were not present. That means their count, you cannot add any counter term. So that's a wrong way of doing the renormalizations. So if you have to, so that's why but as you know, in that part, in a renormalizable theory, when you work with, if you do the quantum corrections and all those things, that the counter term that you get actually, they are corresponding to the operators present in the Lagrangian, right?
Yes.
But here in the effective field theory, that renormalizations occur order by order. Let's say if I'm working a dimension 6, I have to add all the dimension 6 operator in a single slot, and then I have to renormalize. If you do not do that, let's say there's actually 50 operators in dimension 6 you have to add, but if you add any 10 operators, then if you perform the quantum corrections involving them, you will generate some more operator and their counter term. But there is no counter term to add cancel them. So their renormalization constants infinite? No. It's your mistake because you have added a subset of the operators. Okay. So similar, but now all these operators in the bottom-up approach are independent. Okay. So now when we calculate the anomalous dimension matrix, what we do, it is not the anomalous dimension matrix calculation is not top-down. It's actually bottom-up. Anomalous dimension matrix.
So in this case, you have to have the information of the bottom-up approach as well, right?
Yes. So now what I did before performing the RG, we have calculated, let's say, standard model Lagrangian, and I add all dimension 6, 15 operators, okay? And then I construct my SMET of dimension 6, and I calculate all the one loop corrections. Now my one loops will not only involve my renormalized couplings, but also dimension 6 couplings. So I get counter terms for renormalized theories as well as the effective operators. And that counter terms will give me the anomalous dimension matrix. So I have calculated 59 by 59 anomalous dimension matrix. Okay. And that now when I'm coming from top down, I will use the same anomalous dimension matrix, because as you know in the RG, whether you're going from top to bottom, bottom to up, the RG quotient is not changing.
Yeah, it should not, but yeah, my initial impression was how this information, if I just only follow top-down approach, how this information will come, but you have to use the bottom-up.
Yes, basically same beta functions, exactly.
Yeah.
Right. And then when the mix, the interesting part, you generate 11 separate operators, but the Wilson coefficient will function of the same BSM parameters, which were appearing in the 37 operators Wilson coefficients.
Okay.
So that's why these are readily generated operators, not through the integrating out.
Okay.
Okay.
Okay. Thank you.
That was your question, right? I mean, this.
Yeah. Thank you.
Okay. Any other question?
The other people participating, they should also ask questions. No,
Yes,
don't
yes.
be just listening.
Not for your sake, but for sometimes for my sake, because then I can take time to breathe also.
Maybe they will have some question later on, so yeah, can continue. They'll have some question later on, maybe you can continue.
Okay, good. Okay, good. So we know a top-down approach, how to integrate out and how this running and all those things are calculated, right? Great. So these are some, when I'm talking about this standard equation of motion, all those things, just to display them, just to give you a flavor, what kind of equation of motion we are using. So once you integrate out, as I was telling, you get an effective action or effective Lagrangian. Or remember, okay, so I'm using the action and Lagrangian density in the same, manner. Okay. So excuse me for that. So now we have this Lagrangian effective action, but we need to sort them in terms of watts or basis or SILH. So what we do, you use this equation of motion. So once you have these gauge fields, scalars, and the harmonic equation of motion, then it will help you to remove the redundancy and to form them and recollect those effective Lagrangian in terms of particular basis or watts basis structures. Because if you do that, then people have already computed the observables in terms of the operators, independent of the theory. But for your theory, if you write down, okay, in the effective Lagrangian, this is my effective operator, this is my Wilson coefficient, if you calculate, then what you will do, you can use that information from the literatures and you can perform the analysis for your models or some preferred scenarios, right? And also on top of that, you have to use some, if you want to go from one basis to another basis, you can use different kind of identities. So these are the basically gauge invariance operators. Now you can see that these operators can be written in this particular form and so on. That's why two different bases and all those things, they're actually taking the information of multi, linear relations among different kind of operators. Okay. Also, you have to use this kind of Pairs identities and so on. But these are all involved in this program actually. So it's good to know what is inside the program, such that you know what you are not missing out actually. Yeah. So this is a nice pictorial demonstration when how do you go from one to another basis and how they're related. So this is the basis where you are working in a strongly interacting light Higgs basis. Okay. And why this basis is interesting? Because if you see is whether you talk about the Higgs physics, okay, and there are a lot of observables you can design, and sometimes from the experimental point of view, some of the signatures are very prominent in terms of SILH operator in compared to the Warsaw. Okay, that's why that is the reason people choose different kind of basis to make the impact of the operators more transparent. Okay, otherwise it is everything's captured is everywhere. But in somewhere it is so masked that it's very difficult to extract that information. Okay, so now this is the SILH one where you have all these operator classes are there, and you have this Warsaw where you have these operator classes are there, but still you will have two more operator classes, which is this and this one. And interestingly, neither of them actually are included in these operator classes. Okay, so now these arrows are showing you how to go from one to another. Okay, so this operator, if you start, okay, so then they are actually assumptions in the multilinear. It's not like a one-to-one correspondence. One operator have a contribution to multiple operators, and that operator again can further bifurcate it and contribute to some other operators. And how these relations are controlled? Nothing but these relations, which are nothing but the related to equation of motion and IDP kind of thing. Okay, so this is just to give you an idea that why these different bases are important and how one can connect to another one. Okay, so now, so far we talk about the simplest cases, okay, specifically for the scalar integrating out. Now I'll discuss about the what are the different kind of features appear when you integrate out heavy fermions. Of course, you generate the previous operators as well, but for the scalar, there's some for the fermion, there's some additional part is there, which is the separating operators. And this, there's a separation. The two broadly you can classify two different kind of separations. Okay, source of separation. One is the spontaneous one. For example, when you perform the spontaneous symmetry breaking, if you do assign the wave to a complex part of the scalar field, then you break the CP spontaneously. Okay, that means your pseudo scalar is basically becoming massive. Okay, but we are not interested in that separations. Okay, we are interested in separation which is more explicit. That means in the Yukawa sector. Okay, your Yuka couplings, there are some, those are matrices. These are matrices in the favor space. Okay, that's why this is 3 by 3. Okay, and as you know, in a 3 by 3 basis, you can accommodate some complex phases in the Yuka coupling, which you cannot absorb by the redefinition of the fermion field. That's why they have the physical effect actually. So I'm talking about the separation in the Yukawa sector, which actually more feasible. Okay. Now, if your UV theory have some kind of interactions, and that involves a heavy field and a light field, okay, and then when you integrate the heavy field, what is the fate of that separation that we have in the UV theory, that you need to know, and that's why you need to understand how the separation is realized in the context of standard model effective field theory. Okay. So in the dimension 6 level, what you can do, you can look into the operators and then you find out these are the CP conserving operators. These are the X cube class. So these are the three field tensors are there. And you see there, basically the antisymmetric structure constants are involved. And then you have the phi square X square class. This is the phi square and this is the X square class. Okay. And these are all basically CP even operators. Okay. But they are accompanied by the CP vaulting operators as well. For example, this operator may have this kind of structure, and because of the presence of the epsilon, mu, nu, alpha, beta, okay, these are the CP vaulting. Okay, so now in the scalar, heavy scalar, when you couple with the standard model fermions, if there is no additional source of CP violations, then what you will find out that in case of heavy fermions, okay, which couples with the standard model scalar sector, if there is a CP violation is there, then upon the integrating out of the heavy fermion, you can generate these operators. And now you must be wondering that why I am talking about the CP odd or CP adding operators, and also I'm talking CP conserving operator. It will be clear because you can really show that unless you do a very, very non-minimal skewed kind of scenario where you perform really some kind of very pseudo cancellation, the CP holding operators will always be accompanied by the CP conserving operators. So the statement is following. You can generate from a UV theory, you can generate CP conserving or CP even operators without generating CP holding operators. Statement 2, you cannot generate a CP vaulting operators without generating the CP conserving operators. Okay, that's why and why this information is important. If you do a bottom-up approach, you treat all these operators independent because you do not have any clue that okay, what is the origin of these operators, and then you to fit some kind of CP vaulting data, you only use that CP vaulting data from the experiment and you try to fit them. But that is not, in my opinion, to do the right thing, because what I'll show you in a pictorial way that these cannot be generated without being generated this one. So let's say, consider a very simplistic scenario, or the distance slightly non-minimal. I don't need to extend by model by these three different kind of vector like fermion. You can play the game and make a conclusive remark with these two. So this we have introduced the vector like electrons. Now what is this vector like electron? And difference in the chiral fermion. The chiral fermion, if you see, they are coupling the left chiral fermion and the right chiral fermion, they couple in a different way. Okay, but the vector-like theories are there where the left and right-handed fermions couple on the same way. They are treated on the same footing. That's why we have two copies. Each one is left, one is right, and they have the exactly same quantum number. And because, as you know, the right-handed objects are nothing but the charge conjugation of the left-handed object, right? So that's why the right-handed object, if you have the same E1 quantum number or same quantum number, then they will be automatically anomaly free. So your gauge quantum number, if you assign by the same vector-like theory, the pair-wise there's a cancellation. That's why the vector-like theories are basically do not suffer from any kind of gauge anomaly. And that is why they're one of the reasons they're very attractive. For example, one of the vector-like theory, which was a left-right symmetric model. You see, you have this SU12 called SU2R theory. What are the fermions and all those things? Your left and right fields are basically exactly on the same footing. That's why there is no anomaly in the, you don't need to even check the cancellation of the anomaly for the left-right symmetry, right? So similarly, we have introduced this vector-like fermion, having this assigned quantum number, y is a hypercharge, you can assign to be 0 or whatever you can. Now, you write down this Lagrangian, and we are focusing on that part of the Lagrangian, which is relevant to us. These are the kinetic terms, and now, these are the Yukawa sector. The Yukawa sector is a heavy fermions, and this is a standard Higgs. And now you can see, if there is no separation, that means basically your y eta L and y eta are exactly same. Okay, that implies there is no separation. But if you want a separation, then your y eta L is not equal to y eta R. Their magnitude could be same, but their phases are different. So the phases of these couplings are different, and that's the signature of the separation in this kind of theories. So now, if I start with this UV Lagrangian, and then I integrate out this thing, what are the possible diagrams I can have such that I can generate those city-heading operators? These are the diagrams. So there are two classes of operators which contain the separation. One is the phi square x square. So you can see there's a phi, and it's the x. And then you have a fermion loop. And these psi1, psi2 are basically my heavy fermion. Now, if you see carefully, you can decompose. So this, if you have primarily focus on this vertex, and you find out the psi1, psi2 is a coupling is basically a plus b gamma phi. And why is a plus b gamma phi? And why a and b are not equal? Because your y eta L is not equal to y eta. So what you do, you write down PL as 1 minus gamma phi by 2, PR as 1 plus gamma phi by 2, and you write down, and then you'll find out your A is basically y eta L plus y eta R by 2, B is y eta L minus y eta R by 2. That's all. Right? And so you have couplings where A is not equal to B. That's why it is A plus B gamma phi. And similarly, there's another vertex, A plus B gamma phi. Now, if you think about in terms of amplitude, you get three different kind of contribution. While you have only A. In one case, another case will be B gamma phi, B gamma phi. In another case, only one is A, another is B gamma phi, and vice versa. Now, what is the meaning of this? If you calculate this, there's a trace because the fermion loop, and there is no gamma phi involved, so you basically get a CP conserving operator. There's a gamma phi here, but there's another gamma phi here, and gamma phi square is basically your identity. Now, if you use that, then you'll see under the trace there is no gamma phi accompanied with the gamma mu. So that means basically you get a CP conserving operators. But in this third diagram, it's linear in gamma phi, there is no gamma phi. So these gamma phi will be accompanied by 4 gamma matrices. Okay, and that inside that trace is basically give you the epsilon mu rho sigma, and that's where you generate basically CP firing operators. So now you can see the same UV diagram is giving you 2 contributions. One is dumped in the CP conserving operators, one is dumped in the CP firing operators. So if you want to make them 0, automatically this term will be 0. So this you cannot have without having this one. These are automatically there when you generate this kind of one. And interestingly, CP firing observers and the CP conserving observers in this particular case, they're function of same parameters, A and B, which are the BSM parameters. So from the data point of view, though there are 2 different set of observers, 2 different set of data, but there is a theoretical correlations. Okay, and that's why understanding these kind of theoretical correlations will give you much more better handle to deal with, and your analysis will be much more robust. Okay, yeah. So any question after this part? Okay. Similarly, there's another operator which is basically x cube plus. But interestingly, x cube plus you cannot generate at the one loop level. You have to go to two loop level. There is no UV theory where you can generate this x cube in the one loop. So there's a two loop diagram. If you compute and decompose in the same way, then you will find out the same thing. The argument will not change. That if you generate the CP hiding operators, that will be accompanied by the CP conserving operator. But on top of that, there's another lesson we learned from here. In the bottom-up approach, when you write down those operators, we treat those operators, on the same footing. That means whether, because we don't know really, right? Because the operators generated at tree level or one loop and those things. So now, when I'm putting a constraint of allowing the range of values for the Wilson coefficient, we allow them on the same footing. But that is not certainly true, right? Because the operators which is generated at tree level and is a 16 pi square times larger than the operator generated at the loop level. So the strength of the Wilson coefficient cannot be on the same footing. So that's why sometimes the bottom-up approach analysis, when you do, and we do this kind of thing, this will lead to some kind of overestimation. So bottom-up approach is always, most of the time, is giving you a very overestimated thing, and it is not suggestive. Rather, I would say this is very wrong. If you translate and use the result of a bottom-up approach fitted data and you translate that for your model, it's a completely misleading thing you will do actually. So bottom-up approach is a good thing to just understand each operator, what is the maximal allowed value you can do, and that may help you to set the prior of the parameters, okay, when you perform the analysis for the top-down for different kinds of scenarios. Okay. Yeah. Any question?
Sir, I have a question.
Yes.
So are you saying that if we bottom-up approach, we do not know effectively what are the Wilson coefficients, and we need to fit that. So we do not know which are the 1/16 pi square subtest. So we may get wrong with Wilson.
Now I'm saying, when you remove them using, okay, they are not part of it or something like that, that is a misleading statement.
Oh, okay.
Before making that statement, one has to be careful whether this operator is generated at loop level or one, two loop or.
Yes.
Maybe more precisely, if we, let's say, have some operator from bottom-up approach and we use the data to constrain them.
Your voice is breaking, Sanjay. Can you please repeat?
Sorry, I'm saying, let's say we have this operator from bottom and we use the data to constrain them, let's say. Up to that point, maybe it's still okay, but the only thing is that if we try to interpret,
that's an overestimation you will do. Yeah. That's maximum overestimation you will do.
Yeah, if we try to interpret them in the context of some model, then
that's
I think that will be wrong, I think.
Yes.
Some of these operator may not be generated. Yeah.
Yes.
With that large coefficient.
Yes. Because, and also see the two operators which are fitting constraint to be independent, but in a top-down approach, as you can see, those
they might be dependent also.
They are related to each other, right? So that means observable wise they are different, but there's a theoretical correlations. Okay.
Yes.
So so like experiments provide a covariance matrix. Similarly, theoretically you have a covariance.
Yeah.
Of the relations that will be missing out, and that's a huge impact. And when I discuss the real analysis of this kind of data, then you see that it's an unimaginable impact between and difference between these two methods.
Yes.
Okay. Any other question? Yes. Okay. Okay. And so so these are the basically if you perform the full one loop matching, and then you'll find out. And from the Wilson coefficient, what I'm saying is basically also reflected there. How? Because if you see the first three operators, right? These first three operators are basically your self-adding operators. And in this case, the Wilson coefficient is proportional to the imaginary part of the y star. And see, these are the left and right coupling. And that's what I said, if you recall, that city phase inside the Y are not same, then only there is evaluations. So if you can write down Y in a parametric form, like some modulus of some quantity times e to the power I theta L, and Y theta is e to the minus I theta, this quantity is basically proportional to e to the power I theta L minus theta. So the city violating phase difference between the left and right coupling is basically a measure of the city violating Wilson coefficient. Now, if I set theta L equal to theta R, what will happen? This will automatically vanish, right? So this imaginary part is basically 0. So that's why they are not generated. That's a nice way to interpret and understand the result. On the other hand, if you see these cases here in the city sector, all are basically Y dagger. So these are basically a real quantities. So even the phases are said to be identical, left and right phases, still these contributions will always be there. Okay, so that's why you can generate the dimension 6 city conserving operators without generating them. But if you generate them, these are automatically there. That is the statement, and there's another way to check it explicitly. Okay, so yeah, so now I'll enter the phenomenology part. But yeah, before entering the phenomenology part, so if you have any questions on the so far in the last 2.5 lectures so far, yeah, 3 lectures almost. Okay, good. So so at this point, we have learned how in a bottom-up approach for a given theory, if I know the symmetry and quantum fields, how to write down the effective operators. Okay, and then in a complementary approach, what are the given theories, the UV theories, how do we integrate them out, and how you generate the basically effective operators. And using these two methods, now we'll see with these effective operators, whether it's generated in a bottom-up approach or in a top-down approach, how our notion of phenomenology got changed. How, as we are claiming, the effective field theory is a tool to, or a method to capture the imprint of some unknown or known UV theories, how we can do that. That is what we'll learn now. So this is the idea of doing that thing. So with the data that I'll be emphasizing more on like a positive data, I would say, which is not a null result, but rather we have observed the electric precision data and the Higgs data. Okay, and then we'll see, we'll calculate the observables of this electric precision data and the Higgs data using the standard effective field theory, and we try to gauge what kind of new physics can be observed. And the experimental that we will be considering in our analysis are lab 1 and lab 2 data, and from the LHC. So that's what I was saying, that we have a theory plus experimental blending, okay, and then we'll try to find out the presence of the new physics within the data. So again, just to recapitulate those things which will be used again. So the effective Lagrangian is basically the universal part and the effective operators. Okay. So when you do not have this term, this you can consider the standard model Lagrangian, and these are the standard model effective field theory that you can add either bottom-up approach or starting from any kind of theory, you generate these operators. Okay. Right. So now, the standard model effective field theory describes and is expected to describe the physics beyond the standard model, which is around the lambda, which is the cutoff scale, or beyond that. And at dimension 6, if we include the favored structures, there will be 2,499 independent and non-redundant operators, but which form the Warsaw basis. But if we are blind to these favored structures, then that will be reduced to 59. Considering that there is no baryon number and lepton number violations, okay, then we'll work with those 59 operators only. Now, when I'm saying the observables, what is the meaning of that? So basically, this is what you observe in terms of cross section, and all those things from the experiment. So this is the data that experiments are providing you, and this is the theory typically you are calculating, right? And then you would expect that the deviation between experiment and theory is basically hidden if it is there on them. And then if there's a deviation is less, that means they'll put a higher constant on them. So they'll push lambda to be very, very high. Or if the deviation is not much, that means basically the lambda is not too high. And that the data will dictate the choice of the lambda. So we start with this 8 different classes of operator: phi 6, phi square x square, psi square phi x, phi 4 d2, and this phi square psi square d, x cube, phi psi square phi cube, and psi 4. These are the 8 different classes are there in the dimension 6. Right? So first, we try to understand that when we include these effective operators, how the spectrum of my theory get changed. What is the meaning of the spectrum? Because in the standard model, when you learn the standard model, you basically calculate the, after the electric symmetry breaking, you calculate the mass of the gauge bosons, the fermions, the Higgs, and all those things, right? So then what we will do, we add the operators, effective operators, and after that we'll perform the electric symmetry breaking. Okay, with the new minimization conditions and so on, and then we'll recalculate the the spectrum. And what will be your expectation? Our expectation will be, if I recalculate the mass spectrum, then the masses will contain 2 parts. One part will be exactly same as the previous renormalizable Lagrangian offers, and some additional contributions which are proportional to 1 by lambda square. That's how we can identify, and they are basically linear in dimension 6 operators. Okay. So this is the chart, or flow chart rather. Okay, just to tell you which operators contribute to the spectrum and how. So you start with phi 4 d2 operator. So this phi 4 d2 operator, once you perform the symmetry breaking, okay, then it will actually redefine your scalar field. Okay, so this is like a field redefinitions you have to do once you include the effect of this operator. Once you have this redefined field, automatically your potential is changed, and also potential now have an additional contribution from phi 6 operator. So renormalizable potential is changed with these new fields. On top of that, you have now additional contribution to the potential beyond phi 4, which is phi 6. So this gives you a new V, and that V, once you perform the minimizations and all those things, you calculate the new vacuum, okay, and from the new vacuum you get the masses for the new scalar fields, and that will eventually give the mass to other fields as well. Similarly, you have the psi square phi cube operator. Once this phi gets the vacuum level, now you can see there's a new contribution proportional to bilinear in fermion field, which directly contributes to the fermion mass. Okay. Then you have this phi 4 d2 operator, which also plays a role in basically contributing mass directly here. How? Because when you expand this covariant derivative, then this covariant derivative contains this. Now you see that you can see the inner structure of the covariant derivative. This covariant now actually contains the similar gauge fields, right? And once you expand them and phi is replaced by the wave, then you will generate a new terms which are proportional to bilinear in gauge fields. And as you know, the terms which are bilinear in gauge fields, they are nothing but contributing the gauge boson masses. So that's the definition of masses, like bilinear in fields. And that's why it contributes in the gauge boson masses. On the other hand, there's another contribution you have to include, that basically you have a phi square x square operator. This phi gets a vacuum value. So this is a modification in the kinetic term. Because the renormalizable kinetic term is x square, but this is an additional contribution to the kinetic term proportional to wave square. And once you have the additional kinetic term, to bring it in a canonical form, you have to diagonalize this mass matrix, kinetic term again, and that's why you redefine your gauge field. Once you redefine your gauge field, all the other terms, renormalizable terms, where this mu is appearing, will be, will have some impact. And then from there, you will generate a bilinear term in gauge fields, and that is a new contribution to the gauge boson masses. In this way, all these different classes of operators actually contribute in your spectrum. Okay, So if you have any question at this point,
You're saying this 5 to the power 4 d square operator.
this one,
Yeah. Apart from
this one or this one?
Yeah, the 5 to the power 4 d square. There
Yes.
are two, right? Same,
Mm.
right? There-
Yeah.
So apart from contributing to the gauge boson mass and giving a renormalized phi, there'll be also a interaction term, right?
No,
Like,
I'm talking about the how the spectrum got affected. Interaction
Okay.
we'll talk about later.
yeah, okay. Acha.
But interaction term, yes, as I mentioned, because the fields are redefined, right? So
Mhm.
they automatically contribute in your Bartes factors. Because your
Yeah, so
Bartes
there'll be if I renormalize 5 times, they'll contribute to the vertex factor, let's say Yukawa couplings and other vertices.
Yeah.
And I'm still saying that there'll be a operator like of class, let's say h to the power 4 d square, where h is you're actually the physical Higgs field, right? That class will be still there, right?
Yes. Because
As a separate interaction term.
yes, you generate new interaction, exactly. Basically,
Yeah.
so for the spectrum purpose, you can think of phi to be replaced by Web, but as
Yeah.
real practice, what you do, you replace the phi not by Web, but V plus H.
Yeah.
And then you extend that operator. Yes. And you will generate some new terms which were absent in the renormalizable Lagrangian.
Yes. Mhm.
For example, you can get H6 term, H5 term, which were absent there.
Yeah. Okay.
Yes. Any other question? Okay, so now explicitly you can see how these things actually work, which I tell as the pictorial thing. So when you have this phi 4 D2 operator, there are two phi 4 D2 operators are there, which is basically H dagger H box H dagger H and this quantity. Once this H is replaced by the Web, then you can see that is a Web square times this thing, right? And now because you have to make it the dimensionless kind of thing. Okay, this is a typo is there. So this should be H should be outside the 1 minus kind of thing. So then you have this basically this lambda V square by lambda square contribution, right? So now if your lambda is very large compared to the V, then this contribution is not very significant. But depending on the precision result, this can be sometimes significant also. This is how that you actually change your Higgs field. Similarly, now your gauge fields from there, when these are getting the vacuum value, then gauge fields are basically, redefined in this particular format. And now you see, now you might be wondering, okay, there's a AMU field is changing to this. May it happen that what about the fate of the goldstones and the photon? Because you have some contribution proportional to 1 by lambda square. Yes. When you have these goldstones, you may find out because you are adding a dimension 6 term. So here, theoretically, you will say 0. What is beyond dimension 6? That means when you work with the dimension 6 Lagrangian, if there is some generated at beyond dimension 6, for example, let's say 1 by lambda of 4, that you will say it's a 0. So that's why in some cases, you may find out the goldstone matrix when you diagonalize, the mass term for the goldstone appears to be 1 by lambda to the power 4, not for the SNET, but for some other cases. Okay, you may find out that thing, but it is not reason to worry because you are truncating your theory at 1 by lambda square. So whatever beyond 1 by lambda is 0, they will be cancelled. For example, if you add dimension 8 operators, you will see the goldstone masses are 0 up to 1 by lambda 4, but you will generate some term which is proportional to 1 by lambda 6. And that's how these things work. And that's true for the fermion thing also, photon also. But in this particular case, if you calculate, you will get exactly photon mass to be 0. So there is no problem with the gauge invariance and all those things. We are consistent with the gauge invariance. So one really doesn't need to worry about. Okay. Okay. So then once you calculate the Higgs mass, then after including all the effects, you will find out this is the tree level or the standard model contribution. Okay. And then you have this additional contribution. Now you see, when you try to fit the Higgs mass, so you have these 3 additional parameters are there, which are basically 3 different, effective operators. Similarly, the W boson and the Z, there are also some additional contribution beyond their regular contribution, and there are dimension 6 contribution. So in this way, you can calculate all the mass spectrum which have, and you can visualize the addition contributions are proportional to 1 by lambda square and linear in these dimension 6 operators. Okay. And in case of fermion, you have this regular contribution, and then you have a C phi h v cube over lambda square coming from this psi square phi cube v cube, because this is a phi cube, right? That's why you get the contribution proportional to v cube by lambda square. And this is the fermion masses are there. And this is if you consider as a flavor indices. So this Wilson coefficient will have a flavor indices as same as the Yuga coupling also. So in this way, you can contribute, the spectrum of these standard model fields, which will go into your calculation, whatever you are computing for the standard model effective field theory. And Sanjay, I think this is the best time to stop, because the spectrum and then possibly will become
okay, fine. Questions and comments from the whole lecture, from the previous lectures?
Yes, whatever you want. Or if you find that one point which is I hurried up, or maybe it's not very clear, you can tell me. I can go back and then explain that to you again.
I have one such.
Go to the slide number 97.
Go ahead, Shubhajit.
Yes.
So like you have redefined this A mu, and now A mu get coupled with Z mu, like after redefinition.
Yes.
Why this is happening? Like,
sorry?
Like why this is happening? Like A mu is the independent field. Now after this, after A mu getting VAPE, like modified A mu get contribution from Z mu also.
Yes, because of course, right? Because you do not have a priori knowledge what is your photon, what is your Z. So what you calculate actually, you have basically your neutral gauge boson spectrum you calculate. Okay, so now once in the renormalizable part, you diagonalize, you have the Weinberg angle, so you have A mu and Z mu. But once you switch on these dimension 6 operators, then you'll find out that neutral gauge boson mass matrix is no more diagonal. It has some off diagonal contribution. So the initial A mu and Z mu are not the physical basis. You have to rotate them, and you have to find out your A mu prime and Z mu prime, and they are your physical photon and the physical gauge boson.
Okay, like unlike the W mu 3 and B mu, now
No,
they are also like
W plus minus, you do not have any mixing, because that's the only solitary case. But here you have a matrix. Right? So previously, the way you go from B mu to W mu 3 basis, you have off-diagonal entities, you rotate them, you get the Weinberg angle and go A mu, Z mu. Now you have addition contribution, so A mu, Z mu matrix is also now have off-diagonal entries. You have to rotate them and go to A mu prime, Z mu prime. And that's why I'll talk about in tomorrow's lecture that Weinberg angle that you have calculated initially with the renormalizable Lagrangian is modified. With the old Weinberg angle, you cannot diagonalize the neutral gauge boson mass matrix. You have to use the new Weinberg angle. That's why Weinberg angle is also modified.
got it.
But that mixing angle will be proportional to 1 over lambda square, right?
Yes. I mean, at normal theta w is theta w plus 1 by lambda square. And that's why, because Weinberg angles are so precisely measured, that's why the electric fission data put a very huge constant on them. But I will discuss the different how to calculate them individually for different processes. That I will calculate. And then I will say what is the value of that.
But even after that, you can still ensure that the photon doesn't receive any mass
in
up
the
to 1
basis,
over lambda square.
Yes. A new basis, my mu prime is 0. That could
up to 1 over lambda square.
That's why the effective field doesn't break my gauge invariance.
There is one question.
Yes.
Can you please explain the part where maybe Joydeep, we can read the message.
Can you please explain the part? Nila bro, can't you ask? Can you please explain the part where there is standard model nucleus contribution in the loop diagram of the around slides by which procedure? This is the question you should not ask, because you are doing the same thing. Okay, that method actually was a functional method, and now what you are doing, the hit kernel, is the same hit kernel method actually you are using. Yeah, you ask Ram Kumar. I think he's in the audience. Okay, so you know this thing. This is our work actually, how to calculate this one loop correction.
Is it your student who is asking?
Yeah.
So, but then you should explain to others as well, even if he is your student.
No, I'm just grilling him for the time being. Yeah,
Okay.
because he is not around. Yeah. Okay, so let me tell others actually how these things work. 67. Okay, so I think there's a. Okay, so I cannot. Okay. The thing is basically, so in the function method, when you calculate, okay, so what you do actually, a priori, you do not consider that which one is heavy, which one is lighter, right? So now what you do, you consider this loop consists of some non-degenerate particles, okay? And then just consider the M1, M2, M3, M4 masses as well. And you compute this loop, okay? And then you take that one of the masses to be heavy, other masses to be zero. Now what you'll find out, the masses which are basically proportional to zero, okay, that will have some contribution proportional to log and so. That's the non-local contribution. Okay. And then you'll have some contribution which is basically still finite, but that should not be there. Okay, I don't know if I am making sense or not, but because I mean in a hand waving argument, I don't know how to present this thing. So for example, okay, so because I have not discussed the heat kind any kind of method. So yeah, so basically what you have to do, you first one has to calculate this diagram separately and you dump the result. Okay, and then what you do, you replace these propagators by their expanded form. So basically get some diagram like this, and you have this kind of loop by the light loops. Okay, and you calculate that loop separately. Okay, maybe I mean, can I use a board then possibly?
You can definitely use the board, yeah.
Okay, because
In fact, I was trying to say that you can use the board maybe.
Okay, so yeah. So let me explain this thing. So basically you have this diagram. Okay, so this is basically the heavy propagators, let's say. Okay, and now once you have heavy propagators, this you can write it down as in this particular form. These are the light and these are the heavier ones. Okay, and now once the heavier ones plus this contributions. So this is the full diagram in the UV, and this is the non-local contribution, and this is the local contribution. So you want basically the local contribution. What you do, you have to calculate this loop separately, you have to calculate this loop separately, and then you have to subtract this from this. And then that will give you this quantity. So that is how these things are being computed. Okay. Is that okay?
Yeah, so you have to subtract this, as you said, this non-local contribution, right?
Yes, because we are interested in the local contribution only. The effective operators is the local contributions.
Okay.
So what if we just like expanded all the like internal momentum, like integrate all the internal momentum, then only we get the
No, you cannot just integrate out. No, integrate has a meaning. You cannot just do forcefully anything. How do you integrate the light propagators? The light propagators are on. You can, what is the propagators you can generate on shell? You cannot integrate out that. You can't expand. You can't perform the covariative expansion on that.
So they're all off shell. Like,
so what? You have to. They are off shell, so you have to perform the expansion, but not in terms of inverse mass. These are having the mass m. So you cannot change the mass parameter. So when you write an off-shell propagator, you do not change that m to anything m prime, right? That's a m. The momentum is basically off-shell. The mass is the same mass, what it has.
then we encounter like logarithm of small mass in terms of like large mass also. Like in the expansion, if I blindly do this loop integral.
Yes, of course, we have the contribution log of m by capital M, but that's the basically inferred signature of the inferred divergence. But as I told you, we remove the inferred divergence because inferred divergence are removed from the matching because it's a property of the low energy theory. So log of light masses are basically signature of the inferred divergences. So we are not worried about them. In fact, if you are smart and then you can make your UV theory infrared safe by using a suitable infrared regulator, then you don't encounter them. They are just dropped out in a limit light mass tends to 0. And actually that's what we do actually. We do a different method called the heat kernel method because that cannot be discussed here now. But using the heat kernel method, actually, you can use a Gaussian infrared regulator, okay? And then you make your theory infrared safe, and then you take safely infrared light masses to be 0, and they do not create any kind. So in our method, actually, you do not even need to calculate those non-local contributions separate and subtract. We contribute only the box kind of things, okay? And with an infrared safe Lagrangian, and then we take light mass to be 0, and then we exactly get the point local contribution. But other people do in a much more tedious way.
Okay, thank you.
Any other question?
Okay, if there is no more questions, then let's thank Joydeep again for today's lecture.
Okay.
We'll meet again tomorrow. At
Yeah,
3.
so
Okay.
tomorrow we'll continue from here.
Yeah.
Okay.
Thank you, Joydeep. Yeah.
Yes, I stop saving. Okay, so stop record.